Hello community, let's crank the intellectual furnace up and let's have a deep dive into the molten core of inference-aware training of our large language model. You know, models like Gemini 2.0 Flash syncing, where we have this inference compute, the test time compute, or think of OpenAI's O1, O3, or think about Qwen QwQ 32B models. We want to see now the improved reasoning, the latest technology. So we have a critical inefficiency, and this is that our LLMs were not trained with the inference process in mind, and I mean here all the other open source projects and open source LLMs. So therefore, we try to go with the latest Google research to have now a look at the new inference-aware training. And this training process now will embed the inference strategy that's going to happen during the test time computation now in the very core of the LLM training methodology. And when I say training, I mean the supervised fine-tuning and everything that goes with reinforcement learning. And you might say, but you have shown us something similar, no? In this video, I showed you here that OpenAI built here on the safety implementation with DA this on a chain of thought reasoning augmentation. But the new paper by Google do something much more interesting. They go here with an inference optimized training methodology for the supervised fine-tuning and the reinforcement learning that is not yet optimized for a chain of thought like OpenAI did. But Google is going really deep and it's optimizing the supervised fine-tuning and reinforcement learning methodology itself for a better inference reasoning performance, and it is not yet optimizing already for a specific reasoning mechanism like chain of thought. Because this might not be the best X of thought mechanism that we can apply. So absolute fascinating. Well, I saw the latest technical reports by Google DeepMind here. I have to show you this. So the central innovation lies here, altering now the training objective of our fine-tuning and reinforcement learning. We throw it out of the window. We have to find here a new idea, and it is called Inference-Aware supervised fine-tuning, the best of N methodology for this supervised fine-tuning that is already optimized for the inference-aware process that happens then in the test time compute. And you know the standard supervised fine-tuning, yeah, but now we want to make it even more interesting, striving to maximize the probability that the expert response would be selected as the best response out of the best of N mechanism. How we do this? Well, unfortunately, there's a lot of mathematics, but it is rather easy if you follow this video. Look, we can formulate this idea in this simple equation where we have here our pi or policy of the best of N strategy represented here, or it represents the best of N policy. But this is now a critical problem because in this function we have some non-differentiable argmax function within the best of N operation. And Google and the researchers of Google had a brilliant idea. They applied a variational approximation. So this new technique now finds here a smoothness to this, and we have now, instead of this, we have a much better solution that we can differentiate. And if you look at this equation, you see here Q of pi. This quantifies the expected win rate of the response Y against other responses sampled from the base policy based on a verifier score. We have to talk about a verifier. That's a very essential element. And the gradient of this new objective here provides here our learning signal. And if you look at this, and I looked at this and I said, I don't understand it. So here is my way to understand it, and I hope I can help you with this. So here we have here this simple formula. And the problem lies now within exactly here our policy pi, where we look here at the best of N strategy. Because, and this policy now involves here an argmax operation. simple form this, but this is, you remember, a discrete operation, meaning we can't differentiate it so easily. And the standard gradient-based optimization methodology, which are our workhorse here in training our neural networks here, rely absolutely on the ability to calculate our derivatives, our gradient operation. And you can't directly backpropagate through an argmax. So the solution was here by Google to have a rational approximation here that approximates here our best of n policy pi with an energy-based policy that is proportional to this equation. And you might say, okay, interesting, I said, and what is this now? So our pi symbol is the base policy probability of generating the response y for a prompt x, and it simply represents the classical initial likelihood of generating that response. But then now, this is now the critical term introduced now by this approximation here, this exponential function. So let's have a look at the elements of this. So at first we have here our q underscore pi, and this here is the expected win rate of a particular response we call y. So it is the probability that the response y may have a higher verifier score than other responses generated by the base policy pi. So formally, we have this expression where our I is here the indicator function. And this is simple. That simply 1 if the condition is true and 0 otherwise. Our lambda of n is a positive constant that depends on the number of samples, and it acts simply as a scaling factor. So for larger n, lambda of n increases, making here the exponential term much more influential in the overall picture. And proportionality here, we need to normalize this expression to get here proper probability distribution, which leads to the partition function z of our best of n supervised fine-tuning objective. So the variational approximation essentially does now the following. It rewards here the winning responses. So this exponential term acts as a reward for responses that are likely to be chosen as the best one. So if a response y has a higher probability of outperforming the other generated responses here, this term will be large, increasing the overall approximated probability of y being here the best of n selected response. And it smoothens here the selection. The benefit is simple. We can differentiate it. This allows us to use here the standard gradient-based optimization technique like backpropagation to train our model. So if I told you you have to throw out of the window our supervised fine-tuning, okay, but not here the gradient-based optimization like backpropagation. This we can use now because we have now variational approximation for us. And then the connection to the best of n methodology is that this approximation captures here the essence of the best of n strategy. As I showed you, as n increases in here, the lambda n, the approximation becomes sharper, more closely mimicking here the hard selection of an argmax function. And this is where we started. So a brilliant idea on a mathematical level. There are several pages in the original papers by Google in the technical papers. I have given here only the shortcut for me to understand it. So let's come now to the main topic. The new best of n supervised fine-tuning objective with this mathematical approximation, you can call it a simplification, that will take care of the inference strategy right at the training level. So here we go. This is here our best of n supervised fine-tuning objective with this mathematical approximation. Let's have a look at this in detail, because I want to really understand this new methodology. Now, Google showed us we can simplify this logarithm, and it becomes now, as I just have shown you, this version. So you can say that this variational approximation is more or less a clever mathematical, I wouldn't call it a trick, it's a transformation to circumvent here this non-differentiable optimization problem in a problem we can solve with the classical tools that we know like backpropagation. So, but this, honestly, I don't understand it. I want to understand what is each term doing in this formula. So I take here this mathematical formula and then I tried here in my simple mind to understand what is it, what is the core of this. So the maximum here, this is more or less the goal, no? Find the optimal policy pi within the space of all the possible policies, capital Pi. Then E represents here an expectation over the training data distribution D. It means we average here the inner expression over all the training examples. But here I noticed, wait a minute, no, I have to improve, I talk to myself, hey, I have to improve because this is already an operator and it's not a function anymore. So, okay, let's start again. Let's go really term by term and make it more precise. So this here is a maximization over the policies, the available policies in a particular space of all the policies available. So this part tells us the goal that we have. We want to find our optimal policy pi for our LLM in the training phase. Pi itself represents, remember, a probability distribution the model uses to generate here responses given a particular user prompt. Capital Pi is here the space of all possible policies the model could theoretically learn and find if it does a search algorithm. And the max means, yeah, we're looking here simply for the highest value. Now, E is an expectation operator if you want to see it on a more abstract level. No? It means we are calculating the average value of the expression inside the brackets over the training data set D. So let's have a look. X and Y simply represent a simple data point in our training set where X here is the prompt and Y is the correspondent expert response by our LLM. D simply means we are drawing these data points from a particular distribution from our training data, the sensitivity to our training data. Or if you want in simpler terms, we are averaging the result across all the examples we use to train the model. Okay. So let's jump into this bracket and really understand what are those 3 or 4 terms are really doing here in the understanding of this. So this is here more or less the log of pi here, a likelihood term. And this is what we have in our traditional supervised fine-tuning. No? Pi is here the probability assigned to our model's current policy pi to generate the expert response given here a particular user prompt X. Log is here the natural log of probability. And what it does, this term encourages here our LLM to assign a high probability to the expert response that we're looking for. No? And the higher this probability, the larger the value of log of pi. So this pushes, if you want, our LLM model to mimic here expert data in the classical traditional supervised fine-tuning. And now we have here plus our first inference-aware additional term. This is new. This is a novel term introduced now by the simplest best of n methodology. You can think here maybe of other methodologies up to Monte Carlo tree search algorithm for the supervised fine-tuning to make here the training process also inference-aware. Our Q is here our expected win rate, if you think about it. Because this is more or less the probability that the expert response Y would be selected as the best response by the best of n mechanism itself. Because it has the highest verifier score compared to the other responders the model pi might generate from the same user prompt X. And lambda of n, as I told you, is simply a scaling factor. So you say, okay, so we have our first inference-aware term in the training phase. And then we subtract here a particular term that has here the log of the partition function. Now, our partition function here this is our mysterious set function that you might encounter if you read the different papers by Google. And it is crucial for ensuring that our approximated best of n policy is a valid probability distribution in a mathematical sense. And why? Because the variational approximation, the trick that Google used here, leads to a score or an energy for each response that is proportional here to this term. And then to turn these scores into the probabilities that sum up to 1, like we know it from the classical way, we need to divide the sum of these scores over all possible responses. And this sum is what the partition function Z represents. And here you have it, where Y dash, if you want, is simply the sum is simply over all the possible responses, Y dash. So this negative log now is kind of a normalizer if you think in the classical picture, no? And by subtracting now here, where is it? Here, minus log. by subtracting here this term, we ensure that the approximated best of n policy, when properly normalized, behaves like a valid probability distribution, probability sums up to 1, that we know from our classical training. So think of it as a balancing factor that keeps the overall probability in check. So there you have it. This is it. And by maximizing now this best of n supervised fine-tuning, this new objective, we are now training our LLM model to not only generate responses that are similar to the expert responses, but also to generate them in a particular way that makes now the expert response the most likely winner when the best of n strategy is applied now at inference time, at test time compute. And this might not be that I understood it immediately. It took some time for me to have a look at this and get the main idea. But of course, as I told you, optimizing the training, we just looked here at the supervised fine-tuning, and you might say, and the reinforcement learning part? Now, we understood here from OpenAI they don't go with DPO, they go here with a classical reward model in particular. And how is Google doing this? How is Google implementing the Inference-Aware reinforcement learning procedure, or the best of n reinforcement learning as they call it? Now, you remember that the traditional reinforcement learning seeks here to maximize the expected reward for a single action, classical. Now, our new Inference-Aware reinforcement learning methodology boldly shifts here the reward focus here to the outcome of the complete best of n process. So the LLM is now trained to maximize the expected reward of the specific responses that the verifier deems here the best from the generated set, and not anymore a single one. And this operation going through a set is the crucial one. I'm going to show you an example in a minute. So this reframes now the learning problem to directly optimize for the inferential outcome. Now, this is not a trivial equation, and I will come back to this, I think, here in a moment. But also I looked and thought about the verifier, and I understand that the verifier is here a real crucial component in the best of n inference strategy, and consequently it plays here a real vital role here in the inference-aware training methodologies, both in the supervised fine-tuning and in the reinforcement learning. But now the complexity goes a little bit up, so therefore I decided, okay, the verifier, if you closely look at it, it is not just a passive component that is used during the inference, but it is really crucial in guiding the training process, both in supervised fine-tuning and RL. Because in our supervised fine-tuning, the verifier score is used to estimate here, as I showed you, Q of pi, the expected win rate of a response. And this tells a model how likely a given response is to be chosen as the best one by the verifier. But how is this done? Not so easy. And if you go here to the reinforcement learning, oh yeah, this is now where the fun starts. So you know what? For this video, I will say, hey, there will be probably a part 2 where we look then in detail also at the reinforcement learning, and then having understood the supervised fine-tuning and the new reinforcement learning methodology, then we will use our common intelligence to try to optimize the verifier for both parts of the training process. But this would be, for the moment, too much for this first introductory video. Short summary. So the core novelty of this approach by Google Research and Google DeepMind and whatever else, lies now in reshaping the training objective itself. So we really touch here the core of the training process. And we want the training process to be explicitly aware of the intended inference strategy that is happening so much later. But if we optimize already the training process for this test time computation, we get the best results. So this is not about, like on the internet you can read, yes, tweaking some new hyperparameters. No, this would be wrong. It is really a fundamentally new choice that we have, altering here the learning objective, the learning goals on a mathematical level. And really the code that we apply for supervised fine-tuning. Now, with my simple mind, I try to come up with a visual understanding to make it easy. And you know what we have in our autoregressive architecture currently? The system predicts the singular best next token. No? We have one token, and it generates the next token, and the next token, and the next best token, and here next only the best token. Now, this is the classical transformer we have today, from entropic to perplexity, whatever you go with. But imagine now, if we go for a best of n optimized, and now we go already to the combined supervised fine-tuning and reinforcement learning methodology, okay, we go with the best, but then we say, hey, we are not focusing on a single answer by the LLM, but we want a best of n. Therefore, we have to have n different versions generated by the transformer. And then we just do not go only for one token step, but we go for a higher complexity. So let's say, just as an idea, in my simple mind, I thought, what if this system decides not to go with the best, but also with the second best? And then the next step is also not the best, but also only the second best, because we have the best of n methodology. And then I thought, you know what? If this is the way, this could suddenly open up here an avenue to a solution that is not only the best here on this level, but it is even better. That is super. This is best plus plus. That would not be accessible if we go with the classical best pathway. Because sometimes the access path to new novel solution are not only to go only with one single choice for the next best token. I tried to imagine this in my simple image here. Imagine we have only the best, and you have transformer architecture where you apply here multiple best of n with this single best of n token idea. So you run, I don't know, whatever you have, Claude Sonnet 3 times on the same identical jobs. But Sonnet, going only for the best and only for the best again, the conversion now of 2 or 3 different runs of the model architecture will more or less converge here in this particular region. It will not give you the identical result. It can't, because it's a probability system. But the area of the solution that, for example, this sonnet will give you, we can locate, for example, here at the border here of this particular potential structure, whatever it is. So you see, if we only go in a linear D-bast only model, we will only discover here only one local min or max structure. So wherever we do the backpropagation, it will not diverge out. Now, I imagine now, and maybe I'm completely wrong, I imagine now if I go not with the best, but here you see this new color, the second best, and I diverge now from the best trajectory, and I explore here different region of the search space, of the policy space. And maybe I go only with the second base. And maybe I discover here a local min-max. Or I go with this second best and I build on this and I discover this local min-max structure in my topology. Or I go with complete other. Maybe I go second best, third best, and then again with the best, and then it opens up the pathway to a super solution. So in my simple mind, I try to understand why is it the case. If I have a classical architecture and then I apply a best of n architecture run, so I take Sonnet and I run it 5 times, the solutions will be different, but they will more or less all focus here maybe on one region in the solution space. But if I bring the best of n optimized into the training process, into the fine-tuning, into the reinforcement learning, the model itself will now, in the inference run, explore here more, in my simple words, min-max configuration in my topology. Therefore, different solution, and maybe one is a gateway to a super solution. So you see, I'm a simple man. This is my simple idea how to understand this also from a kind of a visualization side. So summary. So what we have a new inference-aware training procedure for the supervised fine-tuning. And we have now our, in the simplest case, best of n. Couldn't be simpler, no? The traditional supervised fine-tuning maximizes here the likelihood of the expert responses, but the new inference-aware supervised fine-tuning cranks up here the intensity, maximizing the likelihood that an expert response would be selected as the best of n mechanism. And this means that the model, our LLM, learns to generate sets of responses, multiple responses, where the desired answer is most likely, probability, to emerge as the chosen element of the best of n selection process. And the same is true for the inference-aware reinforcement learning, but I have not found yet there a good example, therefore video 2, hopefully coming up in the next days. So, in conclusion, Google has here this beautiful idea of a complete new inference-aware training process. And it really represents here a fundamental shift in how we do here the LLM training itself if we want to have this high reasoning performance like the O1 or the O3 system, or QwQ by Qwen, or the Flash Gemini thinking model by Google. So I think this is now really, as they said, unlock here this latent potential within our LLMs if we improve the training procedure of the LLM, and we know we want to have this reasoning capability during inference time. So it is not just getting better results with the existing inference methodology, it is really here about training the LLM to inherently leverage those methodologies much more effectively. You learn from a bunch of solutions, and not always a single solution is selected, learning thereby kind of, and Google calls this a meta strategy. And this term of meta strategy rings a bell, let me explain in a second. And Google tells us, this is kind of igniting a new era of LLM development and training, where the training and the inference dance is in perfect synchronicity. So we have, if you want this beautiful reasoning inference of O3 models or of Flash thinking models, the training process has to be resort optimized for the inference causal reasoning. And this meta strategy, this rings a bell, because you remember this video just days ago where I read here the safety instruction, how they are implemented here in the O models by OpenAI, and O3 Mini was given as example. This chain of thought, this reasoning procedure, you could also see it as a kind of a meta strategy, not meta the company, but as a above level strategy. And then you think about here that OpenAI and now Meta, and they moved here from the large language model to improve the performance of AI. They moved here to these large concept models. And in this video, I showed you what is a concept according to the code implementation by Meta. Also, a concept, if you want, is a higher level aggregation of a strategy, of a policy that you want to implement. So this meta strategy now by Google, I have a feeling that all of three, they are moving somehow in the same direction of further development of large language models and vision language models. So absolutely fascinating to read this. This is day one that I read here, the latest paper by Google. And if you want also to have a deep dive into mathematical models, I would recommend you start with this paper. Inference-aware fine-tuning for best of n sampling in LLMs. Those are the authors: Google DeepMind, Google Research, December 18. And here you have the link if you don't find it immediately. They give you a lot of further mathematical proofs, because what I've shown you here, and I told you this is a solution, you have to mathematically prove that this is really a solution and that it's not valid for a specific boundary condition, but it is a general solution. So if you have a look at this paper, you understand immediately the beauty that Google DeepMind really went here to the core of the training process, and not like OpenAI, just doing this for the reasoning strategy of chain of thought. But they really optimized the inherent, the core process of supervised fine-tuning and reinforcement learning. And if you're interested and this video gets some likes, I will have the next video on the advanced reinforcement learning methodology here by Google. So you see, absolutely fascinating times. You don't have to wait till 2025 for new innovations. My goodness, it is now between the years after Christmas, but before New Year. And Google now shows us what can be done. And I think absolutely fascinating. So this is it at the first day after Christmas. And I hope you found it interesting. And it would be great if you subscribe. I see you in my next video.